Ivan, thanks so much for accepting our invitation. So let me first briefly tell you a little bit about Ivan. So Ivan was an assistant professor in the department of condensed matter physics at the University Autónoma of Madrid from 2002 to 2006. Afterwards, he spent 2 years as a group leader in the Max Planck Institute for Solid State Research in Stuttgart. And afterwards, he came back to Madrid as an associate professor, first as Ramón y Cajal fellow, and afterwards as a permanent associate professor at the University Autónoma of Madrid, and it was in 2013. So the research direction of Ivan focuses on understanding the properties of nanoscale systems using scanning probe microscopy, and in particular, he has been leading one of the most exciting experiments on atomic control in graphene systems. And in particular, he demonstrated a few years ago a really beautiful experiment where single hydrogen atoms can be deposited in graphene and create magnetism in graphene. And he has been also leading many other efforts in nanoscale control of graphene, both on the magnetic properties, superconducting properties, and so forth. And today, Ivan is going to tell us about nanoscale control of new properties added to graphene, including superconductivity, magnetism, and electronic gap. So with this, Ivan, thanks so much for accepting the invitation. We look forward to your talk, and the floor is yours.
Okay, thank you very much, Jose, for this very nice and detailed introduction, and also you and Peter for organizing this very nice series of talks that I think we are all enjoying a lot. So as Jose said, today I'm going to talk about the recent efforts we do in our lab, trying to add new properties to graphene, to add them and to control at the atomic scale, new properties that are absent in the pristine version of graphene. And in particular, today I will show you how we have succeeded in inducing superconductivity, magnetism, and electronic band gaps. So we have been working for quite some time on graphene, and now I think we have reached a very good degree of understanding of how really to modify and control new properties in graphene. So I will start with very brief experimental details. So the experiments have been made in a home-made ultra-high vacuum low temperature STMs. You can see here the design. This means all the sample preparation and measurements are done under ultra-high vacuum conditions, and we can measure at temperatures as low as 3 Kelvin. And well, this system was designed and built by Miguel Moreno Ojeda during his PhD thesis, and all the experiments that I will be showing today have been measured in this particular machine. So for as graphene, the experiments that I will show you here have been measured all in epitaxial graphene in the silicon carbide system. So in silicon carbide, it's a polar surface. This means if you go to one side of the silicon carbide, then you have the silicon terminated phase, which is here, where you have essentially monolayer and bilayer regions. So these monolayer and bilayer regions are electron doped due to the charge transfer from the substrate, okay? But in today's talk, I will essentially concentrate on results measured on the carbon-terminated phase. So you turn around the silicon carbide, and then you have that the last atoms which are on your substrate are carbon atoms, and then when you grow graphene, you can grow from one layer to many layers, and these layers grows with different rotational angles, and when you have something like 5, 6 layers, the uppermost, the surface graphene layer, it's undoped. So the Dirac point is at the Fermi level. So for today's talk, we wanted to start with a system which is very close to an ideal graphene layer. It means to an undoped graphene layer, and to this end, it is very appropriate to have this subset because it's a very good approximation to, let's say, ideal graphene. So let me elaborate a bit more on this. Let me show you how we can use this system to have a system that behaves as freestanding graphene or close to it. So that's monolayer graphene. That's the band dispersion for monolayer graphene. We have the Dirac cone here, okay? And this is the density of state that you get for a single layer graphene, okay? That's DFT calculations. So now we want to investigate a system which is as close as possible to this one, but we want to do STM. So we need to place it in some place. Okay, in principle, you can do also freestanding, but this is very complicated. So we want a substrate, but a substrate that do not perturb graphene properties. So a very good trick, our trick is to have two graphene layers which are well rotated. Okay, so twisted graphene layers. So now we are all aware of the works of the magic angle graphene. So in magic angle graphene, it means you have two layers which are rotated just 1 degree. And then you have a lot of electron-electron coupling between both layers. And due to this electron coupling, you have the appearance of very interesting phases as superconductivity of magnetism. But here we go to the opposite limit. Instead of rotating 1 degree, we rotate a lot the graphene layers. So once you rotate the graphene layers more than 10 degrees, the graphene layers become electrically isolated from one from the other. Of course, for low energies I'm talking. So now here in blue, you have the calculations for the twisted bilayers, and that's for a 13 degrees rotation. And then you can see that the band structure at low energies is essentially identical to the one of pristine graphene. And the same happens for the density of states. So that's a very good approximation for freestanding graphene. And the good news is that this kind of samples, we can have it in practice, because if you grow graphene on the silicon carbide phase, then graphene grows with these different rotational angles, and then you can found on the surface regions which has this large rotation angle. And with STM, you can measure the Moiré periodicity. With this, you can know the angle. This is an experiment measured on a graphene layer which is rotated 13 degrees. And then if we measure the IDV, we can see that really we recover the properties of freestanding graphene with the Dirac point at the Fermi level. And of course, this has also been measured by other techniques as photoemission. We see here the very nice linear bands that you get on this system. So the message we have to get here is that if you have two graphene layers which are rotated more than 10 degrees, this is a very good approximation to, let's say, ideal graphene. And that's the starting point of almost all the experiments that I will be showing today. So before starting with the experiments where we saw how we can modify graphene physics, let me show you how deep one can go to understand graphene physics using STM. And in particular, here I will show you how we can use quasiparticle interference patterns to probe the special symmetries that the Dirac quasiparticles have on graphene. Okay, so we all know what the quasiparticle interference patterns are. Just a quick reminder: in these QPI patterns, we see essentially the elastic scattering of quasiparticles on the surface with the different defects that we can have on a surface. In this seminal work by Cromi and colleagues, we can see the standing wave patterns that are formed on step edges or on different point defects that we have on the surface. And it was shown by Cromi and colleagues that analyzing these standing wave patterns as a function of energy, just measuring the period of these standing wave patterns, we can recover the band dispersion of our surface quasiparticles. In the copper surface, what we have is that copper behaves as a two-dimensional electron gas, and then when we map the dispersion, we recover a parabolic dispersion. As I tell you, just analyzing this pattern and measuring the period of these standing waves. Okay, so we will use the same approach to probe the properties of graphene, and then here is the band dispersion of graphene with at the K and K prime points we have the Dirac cones. So this is the complete band dispersion. If I make a zoom for low energies, we see very nicely how the Dirac cones appears both in the K and K prime points of the brilliant zone. So now, for example, the shape, of course, the shape of these Dirac cones will be different from monolayer and bilayer. In monolayer, they are linear, so we have massless Dirac fermions, and in bilayer, you have some dispersion, which means you have massive Dirac fermions. And of course, We have also colors here in the bands, which account to the additional degree of freedom that quasiparticles have here, which is the pseudospin. Okay? So now we do these QPI measurements, both on monolayer and bilayer graphene, and to analyze those QPI patterns, the standard way of doing is to get the Fourier transform, the two-dimensional Fourier transform. And then we get a complete map of many frequencies where we have the different scattering events of quasiparticles with the defects that we have. So for example, if I concentrate in this high frequency region, this is ring-like features that you see here, those scattering processes correspond to electrons which change the valley. They go from valley K prima, for example, to valley K, as you see here. This is known as inter-valley scattering processes. The electron goes from one valley to the other valley. If we now concentrate, for example, in the low frequency region, this ring that you see here, this corresponds to intra-valley scattering. This means the quasiparticles goes from one branch of the cone to the other branch of the cone. This is the back scattering, okay? But it doesn't change of cone. You stay in the same K or K prima point of the brilliance zone. Okay, so those are the two kind of processes that we have. And if we analyze this QPI now as a function of energy, these rings change of size, and by analyzing the diameter of these rings, you can recover the band dispersion of both monolayer and bilayer and the most important parameters. Okay, so that's for the band dispersion, but it's not only how the bands disperse, whether they are linear or massive. It is also that we have this additional degree of freedom, which is called the pseudospin. And it will be how this pseudospin rotates and the conservation of this pseudospin, the responsible of many of the important properties of graphene. And for example, you can see here how this reflects in the QPI. In the case of in the case of bilayer, we see this ring which correspond to intravalley scattering, but in the case of monolayer, this ring does not exist. So we are not sensitive to intravalley backscattering here. And this is because of how the pseudospin is of monolayer and bilayer graphene. So we are somehow sensitive to the pseudospin with STM. So then how the pseudospin rotate reflects on the appearance of the very phase of graphene, which is pi on the monolayer case, and it's 2 pi in the case of bilayer. So now I will show you how we can use STM to probe the very phase of graphene without using a magnetic field. So first, a quick reminder.
Sorry for interrupting. There's one question in the chat, which is what limits the approach of the Dirac point in the upper picture?
What limits the approach to the Dirac point? Okay, that's a good question. So in our case here, when we try to measure at lower energies, we lose the signal coming from graphene because we start to get a lot of signal from the substrate. Those measurements are essentially the only ones that I will be showing on graphene grown on the silicon phase. So here we have the substrate, which is just close by, and we have those electrons which were going to the graphene layer. This is why we have it doped. And then when we try to go to these voltages, we start to see signal from the substrate. So we cannot probe essentially graphene. We lose the signal from it. So that's, I hope this answered the question. Okay, so we wanted to measure the Berry phase. So we first need to know what the Berry phase is, of course, for electrons. Okay, the Berry phase is a phase that an electron accumulates when it makes an adiabatic motion on a material, and then it comes back to the same position. So when it makes this adiabatic trajectory, a closed trajectory, and it comes back to the same position, it might have accumulated a phase. And the phase that it accumulates, it's called the Berry phase, which depends on the topology of the system where it makes the closed trajectory. Okay? So in graphene, this is closely related to the pseudospin and how the pseudospin rotates. Okay? So in the case of the monolayer, the pseudospin makes one turn, rotates once. This is what is called the pseudospin winding. Okay? Rotate once along the K point. So it corresponds to a Berry phase pi. when we go to the bilayer, the pseudospin rotates twice around the K point, so it corresponds to a Berry phase 2 pi. On contrast, if we compare to a standard 2D electron gas, as we saw in the copper at the beginning, so there is no pseudospin, so this corresponds to a trivial 0 Berry phase. Okay, and this Berry phase is key for graphene. For example, it was only when the anomalous quantum Hall effect was measured when people believed that it was an ambiguous proof of the existence of monolayer and bilayer graphene. And this anomalous quantum Hall effect essentially reflects the Berry phase pi and 2 pi of graphene. So the Berry phase was the one that made everyone believe that it was really possible to isolate graphene. And also, due to the Berry phase, it is very difficult to confine graphene massless Dirac quasiparticles. For example, if you try to use electrostatic confinement for massless quasiparticles, it will always be a direction where electrons can escape. So it is very difficult to confine them with electrostatic potential. And a related issue is weak anti-localization, which says that backscattering cannot exist for many types of scatterers, so it really affects and influences the transport properties of graphene. So let's go to our approach. So I am not claiming to say that we are the first, of course, in measuring the Berry phase of graphene. I'm just showing here a new way of measuring without the need of a magnetic field. So as I told you, the Berry phase is the phase that an electron accumulates if you make a closed adiabatic trajectory. So the standard approach to do so is to apply a perpendicular magnetic field, and then you have the cyclotron orbit where the electron makes this closed trajectory, and then it might accumulate a phase, and then you can probe whether it has done or not with applying perpendicular magnetic fields. So here this is the general belief that you need to apply these magnetic fields, but we saw here that it is not necessary. You can apply a trick. We have graphene, and what we do is to put a single scatter here, a point defect here. And in our case, this is a hydrogen atom. So now electrons comes from all directions and they scatter against this hydrogen atom that we have here, and they get reflected on it. So instead of circulating the electron, what we will do is to circulate our tip. So we go with our tunneling tip, and then we measure the scattering events along all directions. And this is equivalent to make the electron circulate. So when we do this circulation, we will analyze just some scattering processes. We will concentrate on inter-valley backscattering processes. So in processes where the electron changes from valley K to valley K prime. And when you make this change of valley, you have that a particular relation between the pseudospin on valley K and valley K prime. And analyzing the interferences between electrons changing from valley, you can know the relation between this pseudospin and you can recover the Berry phase. So let me repeat this, but with a movie which helps us to understand what I'm telling. So here in this purple ball, it's the STMT. So this will be an incident electron, which goes in this direction. Here in gray is the momentum, in blue is the pseudospin of this electron. Then it goes to the hydrogen atom, it gets a backscatter, inter-valley backscatter, okay? Then it changes its momentum, and also the pseudospin change is its own here in red. Let me run the animation. So the tip goes on different direction, the electron, which is going always with this momentum, and the pseudospin, which is locked, and then it gets backscatter, okay? And also the pseudospin rotates. So again, let me run it. So we can see that it's backscatter, and by analyzing just these processes, we can learn about how the interference is due to the existence of this relatively phase between the pseudospin. So how we do this on practice, how we analyze just these inter-valley backscattering processes. So with the Fourier transform, as I was showing you at the beginning. So that's the STM image of our defect, and that's the Fourier transform. So now if we want to check just inter-valley scattering processes, we have to check on these high symmetry points where the root 3 is. And then if we make a pass filter of just this region, that's what we obtain. We see a series of standing waves patterns here, this wavefront. This is the root 3 wavefront corresponding to intervalley scattering. And then here, on the middle, on the position of the hydrogen atom, we see the appearance of two dislocations in the wavefront. Okay, this will be crucial. So here it's for this direction. If we analyze this other direction, again, we see the appearance of this wavefront and also the two dislocations. And if we go to the other directions, we again see the two dislocations. So it is the existence of these two dislocations which tell us that the Berry phase of graphene is pi. So analyzing the fact of having always two dislocations around the hydrogen atom, it's a direct measurement of the Berry phase pi of monolayer graphene. Okay? So the message here is that we can obtain the Berry phase using STM without applying the magnetic field. And the only thing you need is a very clean surface. You need not to have any other absorbates, because if not, the Fourier transform get messy, but then you have two absorbates here, for example, far away, and then you can measure here the two dislocations in one direction, and here the two dislocations in the opposite directions, because they are on opposite sublattices. Okay? So with this, I will go to the part where I explain how we can now modify the properties of graphene and how we can control these modifications using STM. So, of course, this is graphene with atomic structure, band structures, and this is the nice properties that graphene has. And now we will concentrate on adding some properties which are absent and will be very interesting to have them. In this particular case, magnetism, electronic band gaps, and superconductivity. So first, let's go with how we induce magnetic moments. So from a theoretical point of view, the way of, or the answer of how to induce magnetic moment, it's very clear. That's the bonding schematics of graphene. And the only thing you need to do is to remove this pi electron. If you are able to remove this pi electron, this blue guy that I have plotted here, then you will have an ampere electron on the graphene network, and a magnetic moment will emerge. Always when you have an ampere electron, you have a magnetic moment. So our first efforts were done with vacancies. We were removing a carbon atom, and we were seeing the magnetic signal that we could have. But today I would like to concentrate on, just to resume very quickly, the results. And I'm sorry, this was the work by Miguel. And here today I would like to concentrate on the work by Hector, just a quick resume with inducing magnetism with hydrogen atoms. So how hydrogen absorption takes place? Well, we have here graphene with the sp2 hybridization. When you absorb a hydrogen atom, it binds on top of a carbon atom, and then the hybridization of graphene change from sp2 to sp3. So here we have the atomic structure. This is the hydrogen atom. It binds with the carbon atom on top of it, and then it forms a covalent bond with it. So in this covalent bond, you need two electrons. One of them comes from the hydrogen itself, and the other electron you are borrowing from the graphene pi network. So this is a very efficient way of removing the blue orbital that we wanted to remove. So once we remove this pi electron, immediately a magnetic moment emerges around the absorption of the hydrogen atom. And this magnetic moment that emerges has a peculiar spin texture, and according to calculations, once you absorb hydrogen on one sublattice, a magnetic moment should develop on graphene on the opposite sublattice. This is how theory tells us that we should observe the hydrogen atom, and that's the signature of having the magnetic moment. Two peaks on the density of a state, one occupied, one empty, which are the two spin components of the spin speed. Okay, so now we do our experiments. We deposit a hydrogen atom, atomic hydrogen at room temperature. Then we have here atomic hydrogen, and it really looks like what was predicted. And now when we do STS experiments on top of the hydrogen atom, we observe the two peaks in the density of a state, one below the Fermi energy, one beyond the Fermi energy, and we ascribe these two peaks with the spin polarized peaks predicted by theory. You can see here that the spin split, the peak separation is around 20 millielectron volts. So let me explain you a bit which is the physical origin of this splitting, because probably the energy scale is not what you are used to. So, okay, what we claim is that this splitting is just due to the electron-electron interactions inside the magnetic state. So that's just Coulomb splitting. So, you know, when you have an orbital and you put inside one electron, that's easy, okay, no problem. If you want to put a second electron, you have to pay some energy because you will have electron-electron interactions, okay? So in a standard magnetic material, the magnetic orbitals are very localized. They have D or F orbitals, as in cobalt or iron, so they are localized to the atomic, to the, let's say, 1 to 1 angstrom scales. So the energy separation between these two states will be very large, will be of the order of electron volts. And here we are talking about 20 millielectron volts. That's almost 2 orders of magnitude less. So a way to make this separation smaller is to make the interaction between the electrons smaller, and this happens when you have a larger magnetic orbital. So if you make it larger, the U gets smaller, and the separation of the states gets smaller. And eventually, if you make it very large, if you separate a lot the two peaks, then you will have a much more modest separation between the two peaks. And that's the situation we claim to have. We say that here the peaks are separated due to Coulomb splitting, and the separation is small because the state is very extended. And since we have a completely occupied and almost completely empty state, we can say that the separation gives us the U. It's given by the U of the system. Okay? So if what I'm telling you is true, what we expect to have is a very extended magnetic state. And that's something we are very good on probing in STM. So that's the absorption of a hydrogen atom on graphene, and we can know with atomic precision where the hydrogen atom is sitting. Just you have these 3 legs, you make lines, and the position where it crosses tells you where the hydrogen atom is. So now instead of just making an IV curve here on top of the hydrogen atom, we make a series of IV curve along this line. So what we will be doing is probing the density of a state of graphene along this line. When we do such experiment, that's the result we get. Now the horizontal axis is distance from the hydrogen atom, and the vertical axis is energy, and the color code is for the density of a state. Yellow, bright yellow means high density of a state, dark blue is low density of a state. So if just to guide the eye now, I will put the position where the hydrogen atom sits. Here is where the hydrogen atom is, and here on purple and green, we have the position of the carbon atoms. And what we can see is that these bright yellow features, which are associated with the two peaks, with the magnetic moments, located at the position of the purple atom. So we can now really see where the magnetic moment is sitting, and if the hydrogen atom is absorbed from the green sublattice, we see that a magnetic moment develops on the purple sublattice. And this is exactly what was predicted by theory. So what our experiment shows is that we have a magnetic moment which emerges on graphene. It has a really large extension, so this is more than 6 nanometers, but it goes more than 10 nanometers. It's really, really extended. But the whole thing, according to theory, has one magnet on board. It's the same magnetic state. So really, really extended magnetic state compared to what you have in standard magnetic materials. So now it is very appealing, of course, to investigate the coupling between the magnetic moments introduced by different hydrogen atoms on the same sublattice or on opposite sublattice, since we will have direct magnetic exchange. But this is already more old work, and I won't show it today, the details. If you want, you can have them in this publication. Instead of this, I would like to show you how we can manipulate those hydrogen atoms. So we can use STM to manipulate hydrogen atoms, which will be useful in the next part of the talk. So here we see how we have a pristine graphene layer, no hydrogen atoms, and now we deposit with the tip 14 hydrogen atoms. And if we make a close look to those hydrogen atoms, 7 of them are pointing up, so they are in one sublattice, and the other 7 are pointing down. And from what we learned of the magnetic couplings, since we have 7 in one sublattice and 7 in the other sublattice, we know that the magnetic moment that it's induced here should be relatively, should be 0 or close to 0. But now we can go with the tip And we can remove all the hydrogen atoms from one of the sublattice, and this is what we do. Okay, we have 7 and 7, and now all the hydrogen atoms are in one sublattice. And we can continue with this manipulation and change sublattice. So we can really manipulate hydrogen atoms and decide where we induce magnetic moments. Okay, so let's go to how we can open electronic band gaps on graphene. I will be using this manipulation of hydrogen. What we will try to use is the quantum confinement of graphene quasiparticles to open band gaps in graphene. So the idea is clear. It's since the beginning of graphene, and usually to do this, what you use is standard lithography measurements. But the problem here is with standard lithography, you cannot go below 10 nanometer sizes. Even now, you cannot go below this. It's very complicated. So of course, STM has something to say this in this lithography methodology. And since the very beginning, there has been tried to lithography graphene using the STM tip. So one of the first experiments was to hydrogenate the whole surface. You make this like graphene, that's the idea behind, cover everything with hydrogen, and then to remove hydrogen with STM tip. You apply some pulse, and then you remove, as you see here. And what they were observing was some changes in the electronic spectra of graphene. So that was the try. So another efforts are here in this work that I'm showing here, where they claim to cut graphene using the STM tip. They do it with high humidity, and they pass a bias here, a tunneling current, and they are able to cut graphene. And well, they measure spectroscopy inside and outside, and they report the existence of gaps. But well, if you look to the spectra, there are faint gaps. I mean, there is a decrease in the conductance, but it's not that the conductance goes really to zero. So much more recently, we had these really beautiful experiments of where they use electrostatic confinement. So this was pioneered by the Stroskio and Mike Skromy's group, where they really made these charts embedded in the silicon oxide, and they were able to doped change from N-doping to P-doping, and this was giving them some electrostatic barriers, and they were able to see these standing wave patterns and really do a series of really exciting and very beautiful experiments. However, those electrostatic confinement has the problem that I was telling you at the beginning, that it is very difficult to completely confine massless Dirac quasiparticles. In some directions, they will always escape. And also, as far as I know, it was not so easy, or it was not even possible to decide which is exactly the shape of your confinement barrier. So we had still some room to do something here in this job. So what's our idea to do this quantum confinement? So our idea is to use hydrogen atoms. If we want to cut the path to electrons, if we want to really cut graphene, so we need, again, it's the same strategy as for magnetism. We need to remove this blue guy. If we are able to remove this blue guy, the transport of electrons cannot take place because everything takes place on the pi bands. Okay, and we know that with hydrogen we can absorb hydrogen, and this will remove these pi electrons. And our hope is, okay, let's use it. We also know that we can manipulate hydrogen atoms individually, as I showed you here. But then the question that we made ourselves is, well, this is atom by atom, but can we really do this manipulation in a collective manner? Can we manipulate many hydrogen atoms at the same time and form structures, for example? And if so, if this is possible, will those structures confine massless quasiparticles here? That's the question we had in mind. So here you have the answer. Of course, it is possible. This is why I am telling you about this. And what you need to do is first hydrogenate your graphene. We do this by exposing graphene at room temperature to atomic hydrogen. Okay, so then this is the result you have. It is very stable. And then we can do our manipulation experiments, but an important remark is we need to be at high temperature. The manipulation only works at temperatures beyond 200 Kelvin, at least for us. So now we are at this high temperature, 220 usually, And then we go with the STM tip, we approach, we apply 4 volts, we make a trajectory, and while we make a trajectory, hydrogen atoms get trapped along the path followed by the STM tip. And then we see that we had here the hydrogen atoms, we do the trajectory, and now we have the formation of this triangular structure. So we have hydrogen barriers. So depending on the voltage and the tunneling condition we use, those tunneling barriers can be as protrusions or as depressions. Essentially, for low voltages, we see here as depressions. And this already is an indication that the density of states here is much lower than in the rest of graphene. It seems like if we are cutting graphene. So let me tell you more about our method. It really works 100% of times, and it's very versatile. We can make the patterning in any direction. You can see here rings, squares, triangles with different orientations. Those are features of something like 10 nanometer size, and we can even erase them. Here I'm erasing this triangle, and then I rewrite, and now I rewrite in a different direction the triangle. So let me show you the animation. We erase it, we rewrite it, and essentially the other structures are not modified. So this works very nicely. So as I told you, we can do essentially any shape, but also any size. We can do very small ones, very few nanometers, and we can go to hundreds of nanometers. We can go even to microns. We are just limited to the scanning range of our microscope. It appears to work in all graphene samples where graphene is decoupled. So we have tried on the carbon phase, on the silicon phase, on multi-layer, on monolayer, on bilayer. Apparently, in any decoupled system, it works. And we can have quite good precision. We call it sub-nanometer precision. If we are very good, really, it goes very, very sharp. But here you can see, for example, a nano ribbon with 4 nanometers width and more than 100 nanometers. We have been able to do 2 nanometers and more than 100 nanometers. That's what we can do. And you can see really the method is really versatile and it works very well, I can tell you. So the question is now, do those nanostructures confine graphene electrons? So to answer this question, we first did some QPI measurements. Here you see a one-dimensional resonator, and then we analyzed the results using a very simple hardware model, so infinite barriers here. So that's the eigenmodes that we expect to see for such a one-dimensional model, and this is the result of our experiments where we very nicely see the different modes. The 4 first modes we can very nicely see. And here we have now a structure. Instead of one dimension, we confine in both dimensions. This is a graphene quantum dot in principle, and then we have the different modes that you could see with a hardware model again, and this is what we observe in our experiment. So we are confining graphene quasiparticles. Okay, so but how good is our confinement? Because we tell at the beginning that we wanted to open band gaps. So in order to open a band gap on graphene, you need that your confinement is very good. Okay, so to do this here, this is a triangle. So first, if I measure an IV curve far away from the triangle, I see this is the standard IV curve for the IDV from graphene, no gap. And now if I make the DIDV inside the graphene, I see immediately the appearance of a very well-defined band gap. And to our resolution, we see how this band gap goes to 0 here. This is a very well-defined. And here we can see beside this band gap, we can see these 2 peaks, which are the first occupied and empty bound state of our quantum dot, of our graphene quantum dot. And by analyzing the width of those states, we can learn about the lifetime of our quasiparticles and how good is our confinement. But of course, as I was telling you at the beginning, we have to do the modifications. In order to do the patterning, we have to be at high temperatures. We usually do them at 220 Kelvin. So then we try to go to the lowest temperature possible to get the best energy resolution that we can do. And the best we have achieved is to decrease the sample temperature around 100 degrees. So the best we have achieved is 130 Kelvin. Be able to stay in the same place for 220 to 130 Kelvin is really a challenge, at least for us. Eva worked very hard to do this, and that's what we get. And we get a broadening of around 40 millielectron volts. And this broadening is essentially the same broadening that you get due to thermal effects. So the only thing that we can say is that our confinement is very good. So it's on our energy resolution. We cannot resolve really how sharp it is, but it appears to be very sharp. So we can say that our barriers confine very well massless quasiparticles.
Ivan, sorry for interrupting, but there are two questions in the chat. So the first question is there any dependence on lattice direction, armature versus zigzag edges? So this refers to the nano ribbon from the previous slide, I think.
You mean here? Okay,
yes.
That's a very good question. Indeed, I have not said because I know it's very complicated, but this is measured on bilayer graphene. So that's the only, with the quasi-particle analysis, this is measured on bilayer graphene precisely to be able to see these backscattering processes. If not, it was much more complicated to see the signal in monolayer graphene, where the zigzag and armature direction, I think, will affect a lot. I think this is the question. And related to this also, well, I think this might answer the question.
Yeah, and then there's another question, which is, would you see effects of electron interaction in your ribbons?
Yeah, the problem here again, it's that the manipulations are done at very high temperatures, and we have to measure at, for example, those measurements are done at 170 Kelvin, if I'm not wrong. So we are at very high temperatures. We would like to be able to measure the same system at 4 Kelvin, for example, and then to analyze with more careful. And this is what we are trying now. We have built a new system where, in principle, we should be able to measure on exactly the same location at 4 Kelvin. So that's the kind of things that we want to do. We have really a lot of ideas to work on here, but we would like to be at lower temperature.
Yeah. And then there's a third question, which is, why can't you cool the system down and repeat the measurements to get smaller broadening? Yeah,
that's the problem here is you have thermal drift. So anytime you change the temperature of any material, the dimension change. So our STM head, it's called a beetle type head. And this is very well drift compensated, which allow us to keep very well the position even if you change the temperature. But usually when you change the temperature a couple of degrees, then your tip stands to change the position with respect to the surface position, and then you completely lose everything. You have to be at a very good, stable temperature. Otherwise, the size of the material changes a bit, and then you lose position. The good thing of the beetle is that you can be very stable for many temperatures. The bad thing is that you cannot retract an approach, or you cannot move X, Y, and decide where you put your tip. So you have to have a compromise. It's really a huge challenge to change temperature and keep the same position in STM. Any more questions, Jose? Or?
Yeah, I think that those are all the questions so far.
Okay.
Thanks a lot.
No, there's one more. Huh?
Oh, one more. Oh, did you? Yeah, that's right. So did you try manipulation with high currents at low temperature?
Yeah. I'm not saying that it's impossible. I'm just saying we did not succeed. We tried, as you can imagine, we tried everything. But when we go, I mean, you go 220 was a very good temperature for us. 200 was still possible. 180 was really very, it started not to be very good. So 220, it worked 100% of time, very reproducible, very nicely. If you go lower, it started to be very complicated. I think you need some thermal activation for the motion. So with the STM tip, you influence somehow, but you need to lower the diffusion barrier for hydrogen atoms to be able to do the manipulation. That's my guess. Okay. So if that's all for the moment, let me let me continue. I think I have shown you that we can really form essentially any nanostructure on graphene, and that those nanostructures confine very well, let's say, graphene massless quasiparticles or even massive quasiparticles. And then we can really do many experiments. Here I show you one, which is we have different, the same triangular graphene quantum dot, but with different sizes. And of course, if we measure here the conductance, we see the opening of a very clear gap, okay? And here we see the distance between the two peaks. if we now go to a larger structure, we should see that the gap gets smaller, and that's what we see. Still a very well-defined gap, but it's smaller now. And we go to an even larger structure, then again a gap, but it gets smaller and smaller. So if we analyze the dependence just as a function of the square root of the number of atoms, that's what we expect for massless Dirac fermions, this is what we get, and we can do also time binding calculations, and we get this very nice dispersion here, the same exactly as we expect, as we have from our experiments. So it is really possible to open band gaps, but there is also many other things. In principle, you could think of coupling the different graphene dots or doing many other different things. So with this, I would like to change to the last topic of today, which is how we induce superconductivity in graphene, and that's again a work by Eva. So how everything started? Well, probably everything started here in this nice SPICE conference in Germany, where I gave a talk about the possibility of how to induce magnetism on graphene, magnetic moments on graphene using hydrogen atoms. Still, our work was unpublished. And then immediately when I gave this talk, one of the organizers, which was Joaquin Fernandez Rosier, came to me and asked me, Ivan, but can't you make graphene superconductor? And then I smiled because first, I thought that I knew that the answer was yes. I think I knew a method of how to do graphene superconductor. And second, because I knew why Joaquin was making to me this question. Just before me, we had Nadia Perch, which gave a very nice talk about the work he made in the Just Danny group, where he reported on the observation of Majorana bound states on change of iron atoms on top of lead. So a change of magnetic atoms formed on a superconductor measured by STM, and you could see Majoranas. So you can imagine which was the idea of Joaquin. So can you form a chain of hydrogen atoms, and can you make your graphene superconductor? So can you go to see Majorana modes on graphene? So when I answered yes, Joaquin, I think I can do, and I was trying to explain him about the technical details. Joaquin didn't care so much about the technical details, but I started to think on how to do the calculation. So this was summer 2015, and then, well, Jose Lado, Jose was also here, and then they started to do the calculation. So apparently they succeed. They were much quicker than we. They published the work already in 2015, so some months, and then they put hydrogen on top of graphene. They plug interactions, so you see the emergence of magnetic moments on graphene, and then you have they add some superconducting pairing, and then you have the opening of a gap, and they show the emergence of Yusheva-Rusinov state. You have in-gap states, which tells you that you have magnetic moments. And that's also very nice because they put a change of hydrogen atoms, and they saw the interactions between those Yusheva-Rusinov states with the formation of Yusheva-Rusinov bands. So you have most of the ingredients required to form Majorana states. Okay, so they were quick, and to us it took some more time because we have just published the paper now, so 5 years almost. And here's how we had in mind to induce superconductivity. So we had in mind to use the proximity effect. So we have deposit lead, that lead is a superconductor below 7.2 Kelvin. So we have this very nice lead island that grow on the surface. We knew this because of our French colleagues, Pierre Mallet and Jean Pellan. And here we can see how the lead island grow. This very nice triangular lead island. So now proximity works that you have Cooper pairs in the lead island, and thanks to this proximity effect, the Cooper pairs can leak into the graphene region. So we expect to have superconducting graphene in the regions close to the lead island. Okay, so to probe this, we have to go to low temperatures. Indeed, we had to modify our system. Now we can reach 3 Kelvin. Before it was only 6, so it was some time effort. And here you can see a lead island, and here you can see graphene. So the first thing we had to check is whether the lead island were still superconducting, because you have also the inverse proximity effect. And then when we measure a spectra, this is what we observe. And essentially we see that superconductivity is preserved, and then if we change the temperature, we see that it essentially preserves the properties from bulk. it is superconductive till 7.2 Kelvin. So now we wanted to analyze the superconductivity that it's induced on graphene. So we analyze the density of a state as a function of distance to the lead island, and that's our result. We see, effectively, we see that we have the opening of a band gap, and it goes far away from the island. This is more than 80 nanometers away. Those measurements are made with superconductive tips. These help us to go beyond the thermal limit, so we can have better resolution than the one dictated by thermal energy. We can have resolutions of, let's say, below 100 micro electron volts. So that's with a superconducting tip. Then if we want to recover the properties without the superconducting tip, we can do either a deconvolution, which we have here, or we can also, in this case, measure with a non-superconducting tip, and that's what we observe on the same, exactly the same line with a superconducting and non-superconducting tip. And well, we can see that we have exactly what we expected from theory. So we can induce superconductivity on graphene. So all these regions here are superconducting graphene. So if now you take a close look to the image, you see like some kinds of line defects on graphene. So here I point them with arrows. Let me explain you what those line defects are. In the graphene layers that we have the simultaneous growth of different domains with growth with different orientations. So when those different domains met, when you have the formation of the complete layer, you have what is called a grain boundary. In this grain boundary, graphene with different orientations meets, you have many undercoordinated carbon atoms, and then you have the formation of a grain boundary. And it is expected that on grain boundaries, you should have localized magnetic moments. That's what one expects from theory and some experimental indications. So let's analyze now a lead island, which is just crossing a grain boundary. So first we see on the lead island, we have the superconducting properties. Then we made a line on graphene far away, and then we see that graphene is superconducting again, even far away from graphene. So we make a zoom of this region to see the atomically resolution on our graphene region, and we can, with this, know that this grain boundary corresponds to two graphene domains that have a different 25 degree orientation, and this is why we have the grain boundary. And now if we analyze even closer this region where we know graphene is superconducting, this is a more clear detail of what we have. And now we are going to analyze the density of a state of graphene along this green line, which is perpendicular to the lead island. So it is at a constant distance of 10 nanometers to the lead island. So if we do the density of states, this is what we observe. So if we want to get now the density of a state of this point, far away from the defect, we just need to make a cut here. If we make a cut on this plot, then we recover the superconducting properties of graphene due to the lead island. And now you want to know how the density of a state is on the grain boundary. We just need to make a perpendicular cut here. And then we see immediately the appearance of these in-gap states, which are UC-Barusinov in-gap states. So those two peaks are these bright yellow features that we see here inside the superconducting gap. So the superconducting graphene gap will be these lines that you see here, and the in-gap states that we observe are these lines. So you can see, if we make a line here around this in-gap state, that the UC-Barusinov state extend very far away from the defect, from the grain boundary, and also that it's modulated with the root-3 periodicity. So those UC-Barusinov states that we have here are peculiar in several ways. First, they originate on a region without magnetic atoms. So here, this grain boundary is just formed by carbon atoms. Second, the magnetic moment, the superconducting properties, it's borrowed from the lead island, which is here. So this is a UC-Barusinov state in a proximitized superconductor. And third and fourth, it extends very far away. It's 20 nanometers is a huge extension for a UC-Barusinov state, and it's atomically modulated with this root-3 periodicity. So very peculiar UC-Barusinov state. Also very important, the existence of in-gap states tell us that there are magnetic moments on the grain boundaries. So this is a direct measurement that you have magnetic moments on grain boundaries. Otherwise, you cannot have states inside a superconducting gap. So let me use the help of theory to try to explain how this Jussi-Barushinov state emerges, because I think it's very illustrative. So that's the calculation for a grain boundary. Now without interactions, without superconductivity. Okay, so when we do this calculation, we see the appearance of a flat state, which means that we have a localized state.
Ivan, sorry for interrupting. I think that we are going a little bit over time, so perhaps you can try to wrap up in, let's say, 2-3 minutes. Is that okay?
Yeah. No problem. I'm just finishing. So this is this flat state, which is this localized state on the grain boundary. When we now introduce superconductivity, we see the opening of a gap. Still, the flat, the localized state is outside the gap. There are no in-gap states. So now we introduce interactions with no gap. Okay, there is no superconductivity, but we introduce interactions, and we see that this band split. We see the spin splitting of this band. And when we introduce both interactions and superconductivity, we see the in-gap state. We see the development of this Jussi-Barushinov in-gap states. Okay, the same as we were seeing in theory. That's theory. So just to summarize this part of the talk, we had an island, this lead island induced superconductivity on some graphene regions, and we had at the same time a grain boundary. In the grain boundary, which the grain boundaries naturally exist on graphene, we have the existence of local magnetic moments, and when we have the coexistence of local magnetic those local magnetic moments and superconductivity, we have the emergence of Jussi-Barushinov states. So we have really the ingredients to do here to have graphene as a very good platform for making, for example, topological qubits or things similar. So I just finished. Jose, don't worry. That's I would like to thank the people who has done the work, the PhD students. Of course, Miguel is not anymore a PhD student. He has really succeeded with his scientific career. He has a permanent position now in San Sebastian, where he leads his own group. Hector, which is now in Alto with you indeed, and Eva Cortez del Rio, which is close to finish her thesis, and Diego, our theory colleagues, Felix, Juanjo Palacios, and Juan Carlos Cuevas for the Autónoma University. They work a lot on hydrogen on graphene, Juan Carlos with the proximity effect, of course, Joaquin and Jose Lado. We work very close together with the work of graphene patterning and also with the work of Jussi-Barushinov states, Vincent Renard, Claude Chapelier, Clément Dutré, and Micha Canelson for the work of the very phase. I would particularly like to thank Jean-Yves and Pierre Mallet. You have probably seen that they provide us the sample, but it's not only this. We have a very long-term collaboration. We go back and forward between different labs. I really learn a lot of physics from them. And today I would especially like to thank Chema. Chema was my thesis supervisor. He passed by some months ago, much earlier than he should have. So he was not only my thesis supervisor, he also facilitated me to come back to Spain. We had really nice scientific discussions all the time, but not only this, he was really a very good friend. And well, I thank him really much. I can really be grateful to him. And well, I also thank the funding agencies and you for your attention. That's all.
Thanks a lot, Ivan, for this wonderful talk and for showing us its really inspiring results on controlling quantum properties in graphene. So now, as always, we have some time for questions. So if you have questions, you can either write them in the chat or raise your hand, and I can perhaps start asking some questions that were in the chat before. So there was a question first, which is about the confined islands. And the question is if it is really fundamentally about the number of atoms or rather the area. I think that this relates to the confinement gaps. Yeah,
okay. Well, essentially, it relates to the number of atoms scales with the area or with the length. Essentially, it's the length of your structures. All are the same quantity at the end. It's the same. It doesn't matter the number of atoms so much. It's the size. It's the size of your system. It's not how many atoms you have. It's the size. But the size is defined here by the number of atoms. The size is what matters.
Thanks. Then there's another question, which is why does the U-Shiba-Rusinov state extend so differently in the two graphene domains?
That's a very good question. So the main fact that the main difference between these two domains is that in this direction, this is what is called the root-free direction. So this is the armchair direction, and in this direction, we expect that all the states, the magnetic state, extend much more than in the other direction, which is I think 25 degrees rotated. So that's just naturally. We also observe this. Here in the calculations, you can see that on this armchair direction, the states extend more. This is due to the interactions on graphene, which are different on the different orientations, perpendicular to the grain boundary.
Yeah, thanks. Then there's another question, which is when you move along the grain boundary, how abundant or frequent are the U-Shiba-Rusinov states?
Yeah, that's a good question. They are relatively frequent, but you can see in this high resolution image, you can see that they are very unhomogeneous. And now more or less we know where we should expect them. We should expect them here, here, here. They're also here. But we have not a clear control of how the atomic structure of this grain boundary is. We have planned experiments to see this. But well, let's say, for example, in this grain boundary, this depends a lot. We will have here, 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 and here. It depends a lot. It's really, there are a lot of different configurations.
Yep, thanks. Then there's another question, which is, can you see sublattice specificity of the U-Shiba-Rusinov states? Grain boundary states, I guess, live only in one of the sublattices.
Yeah, I think this is essentially what you see here. This root-free modulation essentially tell us that we are always in the same sublattice. Always in the same sublattice, we have a highest density of state. And that's exactly what happens in the calculations. So the same is reproduced for the calculations, and that's what we observe here. Always in one of the sublattices. It is very clear seen even in the image, we see that the peak is much higher than in the other one. Essentially, it is located on one of the sublattices.
Yeah, thanks. No, so now there's a question by Jens. Jens, please go ahead.
Yeah, hi, Ivan. Thank you very much for this really beautiful talk and cool results. So I have a question concerning this perspective that you mentioned. Of course, you want to, let's say, build chains and go towards this direction of topological insulators. But is there some theoretical proposal or plan how you get the spin-orbit interaction large enough, or
well, that's
let's say induced spin sparkles, which you would also need for this?
Yeah, that's a good question. That's probably more a question for Jose than for myself. But yeah, I think experimentally, I think we know how we could induce some spin orbit. I think I won't say that that's not so complicated. We have seen experimentally how complicated it is, but I think we can put graphene on top of something. We have very good ideas for this, which could give some spin orbit coupling. Whether it is enough or not, it's a good question. Frankly speaking, I'm not sure. But well, spin orbit, I think we will be able to have it. Whether it is enough or not to form this Majorana, let's see. I'm more worried about the fact of building the chain with atomic precision large enough. That's my biggest concern.
Mm. Okay. Yeah, thank you.
Welcome, James.
Yeah. All right, so we still have several more questions, but since we are going a little bit over time, I would perhaps suggest that we can now close the official part of the colloquium, but we can keep going with the questions after closing the official part. So again, thanks a lot, Ivan, for this wonderful talk and for showing us these really inspiring results. And thank you, everybody, for coming to the colloquium.